Okay, we have been discussing several concepts, starting from kinematics, and we studied dynamics, and eventually we started the energy and the potential energy. Now, before continuing with our discussions on the potential energy, let's see how these things work in action. Now, I will be analyzing a particular kind of motion, the projectile motion. We can look at how the various coordinates change, how the kinetic energy changes, how the potential energy changes, by just analyzing a movie. Well, movies are nice in this sense because a movie is nothing but just a successive pictures. And from each one of the pictures, you can measure the distances. And by just determining which picture you are looking at, you can just measure the time. So movies allow you to measure the time and also the distances. Now there is a software that I like this called Tracker. And it does this automatically. So that is the software I will be using. There's already a recorded video of a projectile motion. So if you just play the movie, this is the motion that we will study. So there's a white pole. Okay, there is this white ball. You just throw it at an angle with some speed. And we already know that at least theoretically it should follow a parabola. That is what we had already studied theoretically. Now let's do the experiment, whether it is actually a parabola or not. Okay, in any system, the first thing we should do, so suppose we want to study this motion. What is the first thing that we should do? Even before choosing coordinates. Even before choosing the point of origin and the point of coordinates. The first chapter. Well, choosing an axis is choosing coordinates. Calibration. What is 1 meter? You have to first define it. So we have to define what is 1 meter. Which length in this video is 1 meter? Well, to help us, there is this stick. Its length is 1 meter. So let's first calibrate our measurements. We have this calibration stick. So this is our 1 meter. Well, it says 100. So let me just correct it. So it is just 1. Okay, so this is your last minute to hand in your homework. Okay, so now we have our calibration. Now we have to choose the coordinates. Well, this is just randomly chosen coordinates. So let me bring it to the beginning of the movie. So let me just move my origin to the initial position. So I have my coordinate axis. One of them I chose it to be horizontal, the other one vertical. And well, you can even rotate it, and this is my origin. Now the next thing we have to do is we have to determine our position. Now this is In this program, at least, it allows you to define a point mass. We will be following this point mass. It also even follows it automatically. So let me just choose the point as my mass. I will be following this mass. I'm not able to. Well, let's see, this is my mass. Okay, it doesn't work. Okay. Now what we will do is we will just follow this mass, and then we will be able to determine its position. It is the speed as a function of time, various components of the speed. Okay, we'll start from here. Until this point. Let's calibrate it. Let's choose our axis. And the origin. Okay, for some reason it became shy of you. It was working in my office without any problems, and now it doesn't work. Now it's rolling. Okay, I'm giving up. I already did that. Not the computer, but the software. Anyway. Homework. I will not accept them anymore. So what we were doing on Tuesday. Now we had, starting from last week, we had defined this concept, the work F.dl from some initial point to some final point. This was the work. And we had also shown that if we calculate the total work done on an object by all the forces acting on the object, we had seen that this is equal to the change in the kinetic energy, where the kinetic energy we had defined as 1/2m, the speed squared. And then we had seen that we divided forces into two different kinds of forces. One of them, the conservative forces, we had seen that the work done as we move the object from some initial point to the final point, we could write it only as the function of the initial and the final points. So in general, we had seen that the work done by a given force as you move from one point to the other point depends on how you go from the initial to the final point. One example was the friction force. We had seen that if an object just stays here, in that case, the trajectory is just a point. Or if you just move the object, start from here, move it to some other point, and bring it back, this is an alternative trajectory with the same initial and final points. Now we have these two trajectories which share the initial point and the final point, but the work done by friction in this case is different. So that's what we call a non-conservative force. We cannot write the work done by friction as such a difference. And there are other kinds of forces like the gravity. We had seen that for gravity we can always write the work done as the difference as a function of the initial and the final points only. It was independent of how we moved from one point to the other one. So if you just calculate the work done on this object as I just move it up and down, or I start from here, move it around, and then bring it back to the same point, the work done is again 0, because the initial and final points are 0, so these are just 0. So this is what we call a conservative force. Now the good thing about these conservative forces is that, you see, if there are only conservative forces acting on the system, the change in the kinetic energy, which we can write as 1 over 2 m v final squared minus 1 over 2 m v initial squared, this is always equal to the total work done on the object. But if there are only conservative forces acting on my system, this total work I can always write as minus u, a function of the final point, plus u, a function of the initial point. And we could also say that one of the kinetic energy plus this potential energy at these two different points they are equal. So this is what we call conservation law. As the object is moving, as time is evolving, the speed of the object might be changing, the position of the object might be changing, but at different times, this quantity will not change. And of course, there might be, this is what we call the mechanical energy. 1 over 2 mv final squared. Now, we had also seen that, plus the potential energy. So this is the mechanical energy of a system. We had already seen that it doesn't change during the motion. So you just pick one point on the trajectory through the motion of the system, measure the speed at that point, measure the potential energy at that point, or calculate the potential energy at that point, then the sum gives you the mechanical energy of the system. And in the absence of any non-conservative forces like friction, this mechanical energy is conserved. If there is some forces like the non-conservative forces like friction, then the change in the mechanical energy will be equal to the work done by the non-conservative forces acting on the system, if there are any. So this is where we had left, more or less. Now, any questions up to here? About the potential energy, mechanical energy, kinetic energy? This one. Other questions? Let's do an application. One is always the pendulum, one classical example. Let us assume that we have some mass m attached at the end of a spring. This is our pendulum. We just move the mass slightly to one side such that it makes an angle theta with the vertical. And then we can release it. What will be its, let's say its speed when it, let's call it theta 0. What will be its speed when it passes through this point, let's say theta 1. So when it reaches this point, it will have some velocity, let's call it v1. What is the speed? Now, of course, we can also study this problem using what we knew before without using potential energy or kinetic energy. We know the forces acting on the system, there is the weight, there is the tension which we have to somehow calculate. And once we obtain the weight and the tension, we will know the forces acting on my system. And if we know the forces acting on the system, we know the acceleration, the initial velocity is 0, we know the initial position. So we can calculate how its velocity changes, how its position changes as a function of time. Now, we will eventually do that, and you will see that it's quite complicated if you don't use the energy conservation. Now, to solve it to find the speed at this point, what we can do is we can still use the conservation of mechanical energy. Because what are the forces acting on my system? there is the tension, there is the weight of the object. Well, there will be a drag force which we will ignore. We will assume that it's negligible. And that's it. Now the tension, the force, the tension doesn't do any work, at least not in this system. Because the length of this spring, we will assume it's to be constant. So the displacement is always perpendicular to the force due to the tension. So it doesn't do any work. Okay, it's a non-conservative force, but it doesn't do any work in this case. So the mechanical energy of the system corresponding to the kinetic energy plus the potential energy due to gravity will be conserved. It will not change. Whatever its value is over here, it will have the same value over here. Now we already know what the potential energy due to the gravity is. Let's say this is our z-axis. So the potential energy due to gravity close to the surface of the Earth, that is important because if we are moving close to the surface of the Earth, the force is constant. If the force is constant, then the potential energy is easy to calculate. And we had already shown that it is nothing but mg times z minus z0. Z0 is just some arbitrary point that you can choose. Because you see z0 is just a single value, you have to fix it once, so that it will be a constant. And why we can just change that constant? Mainly because of this definition of the potential energy. You see, the potential energy, the only thing we can measure is the work done by the force. If we know the force, we can calculate the work done by the force. This is the only measurable quantity. This quantity is the difference of the potential energy at 2 points. We cannot directly measure the potential energy, but we can only measure the difference in the potential energy. So if you just add some constant to your potential energy, it will not change the differences. So that is why this point z0 is arbitrary. If you just change this z0, you are just adding or subtracting a constant to the potential energy, and that has no effect whatsoever. Okay, what is your favorite valve position for z0? Ground. Okay, so you want, let's say this is our ground. This is our ground level. And this has length, let's call it L. This is H. So you want to complicate your life. Okay, so what is the initial potential energy? Well, let's see. This length is L times cosine theta 0. So this is over here is H minus L cosine theta 0. So the initial potential energy is mg times H minus L cosine theta 0. Now the final potential energy, it basically has the same expression. The only difference is that instead of cosine theta 0, it makes an angle theta 1. So the initial mechanical energy of the system. What is its initial kinetic energy? I started from here, I was holding it, it was not moving. So its initial speed is 0, so initial kinetic energy is 0. 1 over 2 m0 squared plus mg h minus L cosine theta 0. Final mechanical energy. Now it is passing through this point, which makes an angle theta 1, and it has some speed v1. So its kinetic energy is no longer 0. The kinetic energy is 1 over 2 m v1 squared plus mg h minus L cosine theta 1. And we know that in this system, Non-conservative forces like the tension doesn't do any work. So the change in the mechanical energy should be zero. Initial mechanical energy should be equal to final mechanical energy because the work done by non-conservative forces is equal to zero. There is a non-conservative force in the system. Tension is a non-conservative force. But nevertheless, in this case at least, it doesn't do any work. So the mechanical energy doesn't change. So 1 over 2 V1 squared plus mgh minus mgl cosine theta 1 should be equal to mgh minus mgl cosine theta 0. So mgh, we can just cancel them from both sides. We can even cancel the masses. They are the commons. So V1 squared 2g L cosine theta 1 minus cosine theta 0. So this is the speed of the object as it passes through the angle theta 1. We didn't need to solve any differential equations. We didn't really need to calculate any integrals. Assuming you remember the expressions for the potential energy for gravity. So it's just algebra. No vectors. You don't have to worry about the adding, subtracting vectors or the components of vectors. They're just scalars, ordinary numbers. And we were still able to determine the speed of the object as it was passing through that point. Now, if we want to obtain the velocity vector, well, from this figure we can see the direction of the velocity vector already. So we already know the velocity vector. We only need to write it down in terms of the components if the velocity vector is required. Note that since the tension is not actually doing any work here, whether you attach your mass to a string and let it move, at this point, when it reaches this point, this height, it will have some speed in that direction, which is v1, or you can just release it from rest, and it will have some speed as it's passing through the same height. And this speed, in both cases, will be identical, because the only difference is the tension force, which doesn't do any work. So whether we are just releasing it or attaching it to the end of the pendulum, its speed will be the same. So these two cases. This is the initial theta 0. So when it reaches theta 1, the angle theta 1, it will have a speed v1, a velocity v1 vector. Now this is theta 0, this is theta 1. Or you can just take this object, just release it. And when it reaches the same height, it will have a velocity, let's call it v2, in the downward sense. And these two speeds, the speeds of the objects will be identical to each other. Because due to the conservation of the mechanical energy, the speeds only depend on the height that they fall through. Only on this height difference. In most of these cases, if the height differences are the same, then the changes in the speed will also be the same. So the changes in the speed squared. So that tells us that the speeds of these two masses will be equal in both cases.
Doesn't the effective gravity decrease because of the vertical component of tension?
Now, gravity never decreases.
The effect of gravity.
The vertical acceleration, you see, in these two cases, the vertical accelerations are different. You see, in this, as your friend points out, there's the weight plus the tension. The tension has a vertical component, so it lowers the vertical acceleration. The vertical acceleration of this object is less than the vertical acceleration of this object. But this object has a tangential acceleration also, whereas this one does not. So the vertical component of the velocity of this object will be less than the vertical component of this one. Well, that is also what we are saying. These two vectors, they have the same magnitude, but they are pointing in opposite directions. So the vertical component of this one is smaller than the vertical component of this one. But this one has also a horizontal component. This one does not have a horizontal component. So these two objects have different accelerations. They have different velocities. So that is in fact what makes the computation of the velocity at each time or the trajectory of this object much more complicated than calculating this one. Nevertheless, their speed, when the height difference is the same, will be the same. It's the same problem when, for example, you throw a projectile. When you throw this projectile vertically up with some speed, when it comes down to the same point, it will have exactly the same speed pointing in the opposite direction. If you throw it in this direction with the same speed, but different velocity because the direction is different, if you throw it with the same speed, it will fall down over here. The velocity will be completely different, but the speed will be identical in the absence of non-conservative forces, if we can neglect the drag force or the friction force. Any other questions? Now let's study the potential a bit more more detail. Let's look at the potential graphs. Now we already know, okay, the constant force, like the gravity, the potential only depends on the vertical height. So it's just a linear function. Let's just assume, let's study the one-dimensional case. Is there just a single coordinate? And in the case of gravity, the potential energy is just a linear function of that graph. In the case of, let's say, the potential energy due to gravity is mgz. The potential energy due to spring is 1 over 2k z squared. So if you just plot them, this is u of z, this is z. This is the potential energy of gravity. This will be the potential energy of the spring. But you can imagine more complicated forces. You can create more complicated forces in which the potential energy graph might have a completely different, quite a complicated shape. Let's just invent one. This is z, this is u of z. Let's just assume that this is our potential energy graph. What is the force? Well, we invented this force. Does it correspond to any physics? Well, if you have heard of Higgs, this potential is related with the Higgs field. But at this level, let's just think that's just something we invent. Now, let's call this maximum over here u0. And let's say that our energy is larger than u0. This is the energy of some particle. And let's just imagine that at t equal to 0, we start the object from this point and it is moving with some velocity v0 in the positive z direction. So what will happen to its kinetic energy as it's moving along the z direction? You see, the energy E is the mechanical energy. One over 2 mv squared plus u of z. So what happens to the kinetic energy as it is moving along the positive z-axis direction from this point? What happens to uz? uz is increasing. You see, from here, if you go to here, uz has a larger value. But if uz is increasing, the sum should be constant. So what happens to v? It should decrease. So at this point, let's just give some names to these points. A, B, C, D. This point is F, G, I, J. Okay. Now at this point, let's say close to the point I, what happens is my object is moving here, the kinetic energy of my object is decreasing, the potential energy is increasing. Well, the kinetic energy is decreasing, it just means that what is the direction of the acceleration? Well, the speed is decreasing, the velocity is in that direction, so if you want to decrease, if the speed is decreasing, that means the velocity is increasing in the opposite direction. This is the change in the velocity, so the acceleration is in that direction. At this point, the velocity is in that direction. This is the direction of acceleration. Now let's say it's moving and it reached this point, where the potential energy is equal to the total energy of the system at this point. So what happened to the kinetic energy? It is zero. It will just stop over there. This is where it stops. At this point, V is equal to 0. Now, at that point, it starts to move. So you see, it's at this point, it is moving in that direction. It will slow down, it will stop, and it will start to move in the opposite direction. Now, why does it start to move in the opposite direction? We will see it in a moment. But for the time being, let's just trust my word. It is move. After it stops, it will move in the other direction. Now, if it is moving in the other direction, it's here moving in the other direction. So what happens to uz? The potential energy at its position. It keeps on decreasing. This is decreasing. So this should be increasing. Its velocity is in that direction and its speed should be increasing. So its velocity is changing in that direction. It's accelerating in that direction. So whether the velocity is in this direction or in that direction, whenever my object reaches this point, its acceleration is in that direction. Now, until the point A, the potential energy will decrease. And the acceleration will be in that direction, in the direction where the potential energy decreases. Well, that also tells me that the force should be in that direction. The force acting on my object should be in the same direction. Now, we will come to the force in a moment. Now, from this point A to this point F, so it's moving in this direction now. It came to this point, it stopped there, and then started to move in the opposite direction. Now it reached this point A. It got faster and faster and faster until it reached the point A. Now from the point A to the point F, no, from the point H to the point F, what happens to uz? I'm moving from H to F. uz is increasing. If uz is increasing, then the speed should be decreasing. So I'm slowing down from the point H to the point F, I'm slowing down. This is the direction of my velocity. If I am slowing down, it means my velocity is changing in this direction. If the velocity is changing in that direction, I have an acceleration in that direction. So from the point H to the point F, my acceleration is in this direction. I'm slowing down, and then from the point F to the point C, what happens to U of Z? U of Z is decreasing. If U of Z is decreasing, then the speed should be increasing. Well, I'm already moving in that direction, and my speed is increasing. That is, the change in my velocity is in this direction. My acceleration is in that direction. From the point F to the point C, my acceleration is in this direction. And from the point C to the point A, U of Z is increasing. From here to here, although Z is decreasing, U of Z is increasing. If U of Z is increasing, the speed should be decreasing. Well, I'm moving in that direction, my speed is decreasing, that means my acceleration is in that direction. The change in my velocity is in that direction, so the acceleration is in that direction. So between the point C and to the point A, this is the direction of my acceleration. So is this clear? So at every point, you see, the interesting thing about the directions of the acceleration is that the acceleration always points towards some minimum of the potential energy. You see here, in this region, the acceleration and hence the forces are always pointing towards the minimum of the potential energy. The same holds in this region, close to this region. The forces always point to the minimum of the potential energy. Now let's do it. Let's formalize this claim. How can we relate the force and the potential energy? Now, we had already been studying systems using the force, accelerations, etc., and there we had to deal with the directions of the vectors. Now we have this nice thing, the potential energy, which was just a number. Vectors carry much more important information than just numbers. For example, vectors have both a number information and the direction information, whereas the potential energy is just a number. It doesn't carry this direction information. Nevertheless, it turns out that the information content of a force and the potential energy are the same. We already have seen how we can drive the potential energy from the force, but we can also drive the force from the potential energy. So to see how we do that, let's just again do a one-dimensional case to start with. Let's just take two very close by points. This is my point P0, this is my point P1. Along my axis, let's say that the difference in the coordinates of those 2 points is nothing but delta x. Now, between the point P0 and P1, I will assume that they are very close to each other. Well, if they are very close to each other, in that case, the force doesn't change. Force is constant. Now, the work done, if we move an object from the point P0 to P1, is nothing but the force times delta x. Because the force is more or less constant in this very small segment. But the force is nothing but minus u of P1 plus u of P2, P0. Now, P0, let's say, P0 is at the point x0, that's the coordinate of P0. P1 is at the point x0 plus delta x. Now from this one, I can solve for the force. Force will be nothing but minus u of x0 plus delta x minus u of x0 divided by delta x. So this is the definition of It's nothing but the definition of the derivative, because eventually we will take the limit delta x equal to 0. This is equal to minus du by dx. The force is minus the derivative of the potential energy as a function of the coordinate. Now let's go back to this graph. From the point H to the point J and even forward, is the derivative of the potential positive or negative? As you change z, potential energy is increasing, so the derivative is positive. But the force, we had just shown that force is equal to minus du by dz. The derivative is positive, so the force is negative, meaning that it's in the minus z direction. So from the point H to this point, there is a force acting on my system which is pointing in that direction. That is why, although at this point my object stops, the speed is equal to 0 at this point, there is still a force acting on my object in that direction, and hence, although it is momentarily at rest, it will start moving in that direction. So this object is moving initially in this direction, then at this point it will stop, but nevertheless there is a force acting on it because the derivative of the potential is non-zero. There is a force acting on it in this direction, so it just comes back. So this is what's called a turning point. My object first moves in that direction. When it reaches that point, it just turns around. That's what we mean by this turning point. And then it reaches the point H. Between the point H and F, the derivative of the potential is negative between these 2 points. So if the derivative is negative, then the force is minus the negative number is positive. So the force is in the positive z direction, and hence the acceleration is in the positive z direction. Then it reaches this point, passes that point. In this region, the derivative is negative. The derivative is positive, so the force is in the negative direction, and between C and A and even further, the derivative is negative, hence the force is in the positive direction, so the acceleration is in the positive direction. Again, when it reaches this point, its speed will be 0, because the potential energy is already equal to the total mechanical energy of the system, so there is no energy left for the kinetic energy. So the speed will be 0, but nevertheless there is a force acting on my system in the positive z direction at that point. So although my point just reaches the point A, it will stop there, and then it will just go back, it will turn around. This is another turning point. So at this energy, my object has 2 turning points. So it will just move between these 2 points. Now, any questions on this one? Now, this is just a hypothetical system. Now, for a more realistic system, for example, we can imagine just take a ball and bounce it. Now, we can model this by just saying that, of course, when the ball bounces from the floor, if there is no energy loss, then the potential energy for this case can be just drawn as this is the potential energy due to gravity, it just increases linearly, and this is the potential energy due to the Earth. So this is the potential energy graph. Just take this ball, bounce it back. So what will happen is, if the energy of your ball is at this level, I just release it from here, it will just come, hit the table and bounce back. So it will just move between these two turning points, this one and this one. And in this case, the relevant distance is just like 1 meter. Other questions?
And jump here and again go towards but this second part of the graph, I don't understand.
This one?
Yes.
Well, this is U is equal to mgz. This is that part. This is the potential energy due to gravity. This is the part that would kind of represent the almost infinite force that the tabletop exerts. You see, the derivative of the potential energy is the force that is exerted on the object. Now, here the derivative is infinite. So that's approximately that will model the force that the table exerts on my ball. Yes?
Anyway, what I want to know is why is the first one? Why is the first one minus?
Why this one is minus?
Yes.
Well, I mean, if you had been the one that came up with this concept of the potential energy, you could have chosen this to be positive plus. It will be up to you.
So the work done basically is to be the difference between two potential energies?
Yes. Why this minus, why the other one plus? Well, because if this is minus, then we can define the concept of the mechanical energy, which is sum of two energies. If you would have preferred the plus sign for this one, then it would be the difference of the potential energies.
So this is easier.
Yeah, convention. Okay, see you after the break.